So on the homework PDF, it says that homework is due at the start of class, but it's not late on Canvas until like midnight. So the objective there is that if we have questions and we want to talk about the homework, I am perfectly willing to commit as much class time as we need to cover the homework in class, but just not the day that it's due. Right? So the day that it's due at the start of class, so that means we're not going to talk about homework questions in class. Does that make sense? So it's a little extra time that you have to submit it or finish the last few problems. Make sense? Okay. So I'm going to submit, I'm going to add homework 2 to the queue. Right, so you'll have another homework to work on in the meantime. All right, so today, the first topic, so I have 2 handouts that I've stopped sort of printing them out because a lot of people are doing digital notes. They're on Canvas, so I'll just display them here as we kind of work through the problems. So if you go to Canvas and Resources, there's a lot of data tables that may be useful to help you along when we get to these things. Most of them I'll point out as we get to them in class. Okay, who's heard of degrees of freedom? Perfect. Okay. So basically, degrees of freedom. I'll cover this quickly because it seems like everyone has some experience with this. So it's the degrees of freedom is equal to the number of equations minus number of unknowns minus number of equations, right? What did I say there? Yeah, I swatched it. Number of unknowns minus number of equations. So we want degrees of freedom equal to 0. That means we can solve it. Right? If the degrees of freedom is greater than 0, we cannot find an exact solution, but we may be able to find a certain series of optimized parameters that kind of get close, right? But in general, mathematically, for the purpose of this class, we can't solve this, right? But there's a lot of scenarios in engineering where we have an underdefined system. So this is called underdefined. But you can actually run an optimization to sort of, for example, like build a polynomial fit that's approximately okay going through all the lines. You know what I mean? If the degrees of freedom is less than 0, this is overdefined. Right? Which means we have too much information. This doesn't mean that you can't solve it. It means that you may not be able to solve it. Right? You can have an overdefined system and still be able to solve it. That means you have redundant information, more information than you need. So I'll give some examples. So if we took a sort of Algebra 2 approach from middle school or high school, right? If I have 2 variables, x and y, and I have one equation, which is a line relating between those. So mx plus b, for example, right? Whatever that line is. In this case here, I have 2 unknowns, 1 equation, so I have 1 degree of freedom. I can't solve this, right? I don't know at what point in this line. There's an infinite number of solutions that are available. For every x, there's a different y. Now, if I add a second equation, okay, I have a solution, the intersection of those 2 lines. In this scenario, I have 2 unknowns, I have 2 equations, I have 0 degrees of freedom. Make sense? Now, let's get into some scenarios that are not so ideal. Now I have 2 unknowns. I have 3 equations. My degrees of freedom is equal to, this is overspecified, so -1, right? I cannot solve this one. There is no single unique solution to the problem. Alternatively, I could also have a scenario with negative degrees of freedom. see if I can draw something there. There is a solution. So just because it's overdefined doesn't mean that there's not necessarily a solution. It just means that two of these equations are the same equation. So in this case here, two unknowns, 3 equations, -1 degrees of freedom. But this is an example where you have redundant information. So for example, in the quiz problem that we had, right, we had the acid balance, the water balance, and the total balance. In this case, the acid balance and the water balance add together to be the total balance. So if you were to solve it with all 3 of those equations, you would still get the right answer because 2 of those equations are actually the same. Right? And one last one. Oh, another example is if we were to have a third axis here, right? So 3 unknowns, so another axis coming out of the page. Then we would, of course, need the 3 lines to link together into one point. And that would be a system of 3 equations and 3 unknowns that you could solve using your linear algebra techniques. Okay. If we have non-linear systems, we can get multiple solutions. Okay. You don't have to have multiple solutions, so that's why the quadratic equation has the plus or minus square root of b squared minus 4ac, right? That's the plus and minus outcome, right? Okay. So in our degrees of freedom analysis, so the video people can't see this, but you get a special performance because you're in class. We're basically trying to solve for all of our unknowns to balance the process. So where do we get our equations? We get material balances. So we get one material balance per independent species. Now the biggest time when this independent species comes up is in the case of air. The flow rate of oxygen and the flow rate of nitrogen in air are not independent, right? They all have that same 21:79 ratio. So you can use either the oxygen, the nitrogen, or the air balance, and you'll get the same result. Okay, so that's an example of when things are not independent. But in the quiz question, the acid and water, those are independent equations. An energy balance is another source. We're not going to talk about energy balances just yet, but it's here just for completeness. Process specifications. This is where we say that the inlet stream was a 20% acid and that the outlet stream was a 12% acid. Physical properties and laws. This could be the density. This could be concentration. This could be vapor-liquid equilibrium. Right? This could be an equation of state like the ideal gas law that relates between temperature, pressure, and volume. Right? So if you know that the system is an ideal gas, then you can do the necessary calculations to convert it to what units you want. And then physical constraints. The most common of these physical constraints is that the mole fractions have to add up to 1. So for example, we made up what a mole fraction is. Right? So the mole fraction of species I is the mass of species I divided by all of the mass together. Because we made up the definition of the mole fraction, that necessitates that the summation of the mole fractions have to equal 1. So that would be the example of a physical constraint. Does that make sense? Okay, so does anyone have any questions or confusions about, so like for example in the quiz problem, if I add together the balance for acid, I add together the balance for water, that's exactly the same as the total balance. So that's why when we're doing these problems, if we have 2 components, we only have 2 independent equations. So we start off with the acid balance, and then we could have either chosen the total balance or the water balance to finish solving it. All right, so that saves us a little bit more time to go through an example. Okay. I think I covered all that there. All right, so what I'm going to do is I'm going to go through a more complicated example than we've seen, but still an example that is one that you'll be able to chew up in a short time as we get more practice with material balances. I'm erasing right now so we can have sort of everything in one place so we can see the development of the problem. Okay, so we're going to do a distillation column. So we have a feed coming into the distillation column. We're just going to draw it as some fancy box, right? You'll worry about this in your thermodynamics 2 and your mass transport and separations class. So a real distillation column has something here called a condenser, right? So the vapors go up, they get condensed, some of them get sent back, and then some of them get pulled off. So this is our feed. Now, for me, it makes the most sense to call that F. This is called the distillate. I'm going to call that D. At the bottom here, we're going to have an energy source. This is called a reboiler. So we're going to be putting heat into the system. This boils the heavy components that sends them up. This chills the light components, sending them down. And that's why we have vapor-liquid equilibrium at every stage. And that's how a distillation column works. And then off the bottom, we pull off the bottom stream. So I'll just call that B. For the purposes of this class, we actually don't care about anything that's going on inside of this unit, right? That is a problem for the junior year. All we care about is this system boundary. Right, so this here has a Q going out. So if we were to do the energy balance, we would have to worry about the heat in and the cooling out of this distillation column. But right now, we're not doing the energy balances. We're just doing the mass balances. So everything that's complex that goes on inside of these processes is not your problem. Right? All we care about is the ins and outs. Your junior year is where you focus on the insides. So if we were to take that general balance equation, in minus out plus generation minus consumption equals accumulation. That is the differential equation that you will derive in heat transfer applied to energy or mass transfer applied to transport. Right? So that same concept that we're doing on a big scale, if you were to shrink it down to a differentially small element, that's how we do diffusion and heat transfer as well. Right? So that's why we like to start big and simple, and you'll zoom in as you move on. So for this particular problem that we're going to work through, we are going to have 1,000 kilograms per second, so a very massive system. It's going to be 10% ethanol and 90% water. We're going to say that the distillate, so 1/10 of the feed goes to the distillate. And that the distillate is 60% ethanol and 40% water. Right, so this would be an example of a problem. The question we are trying to answer is what percent of ethanol is lost in the bottom stream. For the purposes of this example, we're going to balance the whole process, but for the purposes of a quiz or an exam or a homework, you only need to use the techniques and strategies to get to the answer that they're asking for. So if this was your design for the distillation column, right, and you went to your manager might say, hey, that's interesting and great. How much ethanol are we losing? Right? Because this is, let's say, the product. We're trying to purify our ethanol, and whatever goes in the bottom stream is necessarily just going to be wasted garbage. Right? So it's lost profit. Right? So that may be an example of what we were trying to do. Okay. So I'm going to switch this sheet here for another example. So this is our single unit material balances process. So number one, choose the basis of calculation. Well, in this particular problem, it was provided for us. The basis was 1,000 kilograms per second, so I just choose the one that they provided. But we could actually solve this whole problem with any arbitrary basis. Draw a flow chart. Okay, so I've drawn the flow chart, but I haven't necessarily filled out all of the details. So we need to fill in all unknowns and derive equations for everything. Okay, so what do we not know about this process? So let's start off with what we don't know. We don't know anything about the bottom stream. So I'm going to do this very rigorously to show you how it can work in sort of a really complete sense, but you don't have to do it this rigorously. So on the bottom stream, I don't know what the total flow rate of the bottom stream is, m dot b. I don't know what the flow rate of the bottom's ethanol is. I don't know what the flow rate of the bottom's water is. And I don't know what the composition is. So x bottom's ethanol, x bottom's water, right? So I know nothing about this particular stream. So I'm going to do some simple unit conversions right now, or simple process conversions. So I have 1,000 kilograms per second, 10% ethanol, 90% water. Well, that's something I can do in my head, so I'll just knock that one out. So this is going to be 100 kilograms per second of ethanol and 900 kilograms per second of water. Right? So that's a simple one that I'm doing. So I'm filling in my process flow chart with the information I know and the information I don't know. The objective here, right, is we're skipping over the convert all quantities to mass or molar because everything's in mass, but I'm getting myself geared up so that I can do my mass balances. So I'm getting everything into the mass units that I want. Okay, so on the distillate here, we know that it's 60% ethanol and 40% water. Right, so I'm just applying this design specification. Right, this is a design specification. This one here, 10% of the feed goes to D. What's an equation that I could write that accurately classifies this information? Yeah?
M dot of F is equal to 1 times M dot B.
I think it's the other way around.
Yes.
This is the one that always gets me, right? So it would be M dot, so M dot of the distillate is equal to 1/10 M dot F. Right? And so this is the trickiest one. So these ratio design specifications are by far the trickiest design specifications. Okay, I always double check. How can I double check this? I'll just throw in, okay, let's say it's 1,000 kilograms. So if I plug in 1,000 here, times it by 10, okay, there we go. That's a smaller number, right? So I always kind of try and double check these particular ones. All right, so then I also don't know, let's see, I don't know the flow rate of the distillate for ethanol, and I don't know the flow rate of the distillate for water. Okay, so you can see I've adopted a clear nomenclature. All the variables make sense. So I have the first subscript as the flow stream, the second subscript as the component. Now, sometimes you can write these as 1, 2, 3, right? As the processes get more complicated, you're not going to necessarily be able to find a cutesy name for all of your process flow streams. You're going to have to just go 1, 2, 3, 4, 5, 6, 7, 8, 9, right, and deal with it. For a simple one-unit process, you maybe can do in 1, in 2, out, right? But in this case, it's feed, distillate, bottoms. It makes it a little bit easier to decipher. But the organization here is very important. Okay, now if we were to solve all of this, we would know the flow rates and compositions of every single stream. Now, this is fully overdefined because I know if I had the total flow rate and the individual species flow rates, I could just calculate what the composition is, but we're doing it very rigorously right now. Okay, so let's count up the total number of unknowns, assuming that you can't do this equation in your head. right, just for the sake of argument here, okay? So we have 1, 2, 3, 4, 5, 6, 7, 8 unknowns in our process. So our degrees of freedom right now is 8 unknowns. So let's start chomping away at our equations. We need to find 8 different equations to balance this process fully. Okay, so we have minus, let's go through our degrees of freedom, swap back here. Material balances, how many independent species do we have in the system? 2. So we have minus 2 material balances. Now, I wouldn't necessarily recommend that we do it this way, but I'm going to write out the material balances now so that I don't have to redo it later, so we can be a little bit more efficient. So in that case, our material balance is going to be m dot of the feed ethanol is equal to m dot of the bottoms ethanol plus m dot of the distillate ethanol. And m dot of the feed water equals the mass flow rate of the bottoms water plus the mass flow rate of the distillate water. Okay, so those are our 2 material balances. Okay, so let's go next. Process specifications. Okay, so what are our process specifications that we have in our system? So this is one right here, huh? Yeah?
Are those the percents, the fractions of the flow rates?
These could be design specs as well. Okay? So we could write out here that minus, and I'm going to say we have 3 design specs. The first one is what percentage of the feed goes to the distillate. So in that case, that is this equation here. M dot distillate is equal to 1/10 the flow rate of the feed. And then these 2 are design specifications. So now the hard part here is how do we get the design specifications into the variables that we're trying to solve for? So I can write 60% ethanol. So I can write this at the flow rate of the distillate ethanol is equal to 0.6 multiplied by the flow rate of the total distillate. Right, so I'm converting all of my process specifications into variables and units that I can now solve for. And likewise, the flow rate of the distillate water is 0.4 times the flow rate of the distillate. Now just quickly, let's double check our units here. This has to be in kilograms per second of ethanol. This is in kilograms per second. So that means that this 0.6 needs to be kilograms of ethanol per kilogram. Right? It's the ratio of the species to the total amount. All right, so we've got 5 so far. Equations knocked out, so we need 3 more. Let's go down our list. Physical properties and laws. Do I have to convert between volume, pressure, temperature, anything like that? In this problem, no. The next one is physical constraints. And we're actually going to have 3 constraints. So I'll write these out as well. We have that the mole fraction of the bottoms ethanol plus the mole fraction of the bottoms water has to be equal to 1. And then we're going to do the same thing with these 2. Right? So what we're going to say, the reason why I moved it from design specs to constraints, because it's all just based on the definition of what a mole fraction is. But in this case here, I put them under design specs because they were provided to us in the particular problem. So the mass flow rate of the bottoms ethanol is going to be equal to the mole fraction of the bottoms ethanol multiplied by the total flow rate of the bottom stream. The mass flow rate of the bottom's water is equal to the mass fraction of the bottom's water times by the total bottom's flow rate. And that gives us 0 degrees of freedom. This is the hard part. Drawing your process flow diagram, placing the unknown variables in the right location with the correct nomenclature, not correct, with an easy to follow nomenclature, converting word problems to mathematical formula. In the case of the ratio here, the ratio one, I promise you will all screw it up at some point. Always double check, right? Then once you list out all of your equations, it's not that bad. Okay, so the question is, where do we start balancing this problem? Should we start here? No, I got thumbs down. Why should we not start here?
All of those equations have 2 unknowns, like we don't know any, at least 2 of those.
Yep, every single one of these equations. This one has degrees of freedom of 2. This has degrees of freedom of 1. I can't solve these equations. Going back over here, hey, I can start to solve some of these equations. Can I solve this one? Not necessarily, right? So maybe this is where I should start. I should choose the equations that have the 0 degrees of freedom. Or if you don't have an equation that has 0 degrees of freedom, then you'll have to set up a system of 2 equations to solve, right? So if you can find 2 sets of equations with the same unknowns, they each have 1 degree of freedom. If you solve those together, then you have a system of equations that you can solve. Right? So the strategy here, let's just start biting off the simple ones. Okay? So this one here is obviously really straightforward. So that means that the mass flow rate of the distillate is equal to 100 kilograms per second, which means that we can figure out the flow rates of the distillate ethanol and distillate water. So that would mean that so let me just write these out here. So this is A is what we're solving first, and then B and C. We're just knocking them down off the list. The mass flow rate of the distillate ethanol is then just going to be 60 kilograms of ethanol per second. So A, B, C, mass flow rate of the distillate water is equal to 40 kilograms of water per second. Okay? So we've checked these ones off. Okay, now what? Should we do material balances or should we do these constraints? Did we actually solve for any of these variables here? No, we didn't touch them. So these are still the ones we don't want to deal with. Now let's look here. So I know the feed of ethanol, that's provided to me in the statement. I know the feed of the distillate ethanol. So this equation right here only has 1 unknown. Same thing with the water. Okay, so let's do these ones next. So this A, B, C, D, and E. Okay. So if we were to solve equation D, it would be 100 kilograms of ethanol coming in, plus our unknown, plus 60. What's a number that adds up to 100 with 60? 40. So that gives us that the mass flow rate of the bottom's ethanol is equal to 40 kilograms of ethanol per second. Can I answer my problem now?
Yeah.
Right? I don't have to solve the whole system in order to finish this problem, right? I can stop right now and I've actually answered the question. What percentage of ethanol is lost in the bottom stream? Okay, now how do I convert that to an equation? Well, I'm asking for, of the total feed in the system of ethanol, how much of it is going into the bottom stream? So the answer is 40%, right? So this is going to be the mass flow rate of the bottom's ethanol divided by the mass flow rate of the feed ethanol. Right? That's the percentage that is in that stream that is being fed to the process. So we have already answered our question. We actually don't have to continue if we don't want to. Yes?
In
I'd say it's probably pretty bad. And this is a complicated system because you can't fully distill ethanol in water. So typically you'd want to distill ethanol to like a 98% or 96% purity because that's the azeotrope composition. And this is the problem with biofuels, is water. Water is the problem with biofuels. And the fact that it takes a lot of energy to do distillation. And in fact, somewhere on the order of like 5 to 10% of all of the world's energy, all of it, is spent in distillation.
Jesus Christ.
It's a lot.
Like ethanol distillation or just general?
All distillation. Refineries, chemical plants, this is the best technology that chemical engineers have to separate stuff. It's reliable. So that's why there's a lot of incentive to build membrane-based separations or selective adsorbents, right? Because this is a big problem. So a liquid-liquid separation is way, way, way more energy efficient. The problem here is that you have to heat and cool the same unit operation at the same time. And as it turns out, when you're heating and cooling at the same time, it's kind of inefficient. The reason why it's inefficient is because temperature gradients result in entropy generation. Whenever you generate entropy, you lose energy. So distillation columns, very, very energy intensive. All right, but for the sake of it, if the question had instead said, balance the process, we're not done. We haven't fully balanced the process. We haven't solved where all the water is. So then on step E, we have the mass flow rate of the bottom water. So that's this equation here. So we're feeding 900 plus some unknown plus, where's the water here? 40. So if we'll do that math, that results in 860 kilograms of water per second in that particular bottom stream. And now we can finally start chipping away here. So we don't know the mole fractions, but we can use one of these two. So, so I'll call this F. And A, B, C, D, E, F, G. Okay. So F allows us to calculate, actually, do we have to solve this as a system? Oh. Let's see, what did I do here? Oh, that's what I did. I solved, actually I didn't use any of these equations. I used mass flow rate of bottoms ethanol plus mass flow rate of bottoms water equals the mass flow rate of the bottom stream, which is then going to be 900 kilograms per second. And then we can just solve for the composition. So X bottoms ethanol and X bottoms water. And if we chug them away, we get 0.956, oops, wrong one, 0.956 kilograms of ethanol per kilograms of water, and 0.044 kilograms of ethanol per kilogram. Okay. So this is a massively, massively overdone example, but I wanted to show you the full rigor of all of the individual steps. If you can do some of the math in your head, you're more than welcome to do the math in your head, right? I didn't, right? And I probably overcomplicated what it needed to be, but if you can do these simple simplifications and you can do your double checks, you're fine. So lastly, let's just do an overall double check of our work. So how can we double check that we did this correctly?
You could put in some of like the basic equations and make sure all the values work, like the overall mass balance, which we don't have on there.
Yeah, the overall mass balance is a perfect one. So I have 1,000 kilograms per second coming in, so that means that these two streams have to add up to 1,000. So I get 100 and 900. That adds up to 1,000. Now I can double check my species balances. I have 100 kilograms of ethanol coming in, so that means that I have 60 and 40. Yep, that adds up to 100. For water, I have 900 kilograms coming in, so that's 40 plus 860. That adds up to 900 Okay, so we've done the double checks. Looks like we've balanced this correctly. This is what we mean by fully balanced. Now, once we start doing energy balances, a fully balanced system also requires temperature and pressure, right? Because the temperature and pressure tells us everything that we need to know about what the enthalpy of the system is. So then we can calculate how much energy these distillation columns are sucking out of our earth, right? Okay, I'm going to assign homework 2. Homework 1 is due on Monday, so that means no homework questions on Monday. So if you have questions, go by email. And yeah, have a good weekend.